Good. So now I want to talk about the mechanics of tracking by association. I have a small example for you here. We will discuss tracking without division. And everything changes if we do want to include division, then it's no longer possible to do this with a plain min-cost flow. So I'm considering 3 time steps here. And as you see, there are 2 detections in the first time step, 3 in the second time step, 2 detections in the final time step. I have chosen 1D space here because it becomes difficult to draw for me otherwise. And I have drawn some putative connections. As you see, I'm missing some. I could have added this one, but again, I've used some threshold and decided that no, that was really too far. And I've written some numbers on these edges. They're invented, of course, but they need to reflect how likely does that association look in terms of cost. So -1 would mean I get a reward of 1 unit if I associate these 2 detections. 0 means I don't, non-committal, could be, could not be. +1 means, yeah, I can make that detection, but it's not that association, but it's not great, and I will have to pay, 1 unit if I want to use it. And now the question is, all right, which of these things should we actually associate with each other? And well, we've learned a few things already. So why not use pairs of frames? And we can try this. I'm using this color. So if I'm using pairs of frames, for example, starting from this one here, well, the biggest reward I can reap is if I use this connection. And here the biggest reward I can get is if I use that connection. And then in the next time frame, well, the best I can do is to use this one and to use that one. Now I have a lot of reward, but I have terminated one track and I've started a new one. And let's assume for the moment that I don't want to allow appearances or disappearances. I don't want to allow birth and death of cells in the middle of nowhere. Let's say I want to track a constant number of cells here. So the solution we have obtained, it's not consistent. Yeah. So it's not consistent across time. So I don't like it. Then, well, if we want something continuous, why not use shortest path? We have learned all that you wanted and some that you didn't want to know about shortest path. And well, if I am looking for the very shortest path, let's just say from left to right. Okay, for shortest path, I always need to say from where to where. Let's say from some source S to some terminal or target T here. And let's also assume that the costs of these first edges here are 0 and the costs of these last edges are 0. Then, well, I think the very shortest path that I can get is this one here. But now I've tracked just one particle. Okay, I could maybe say, all right, fine, let's look for the second shortest path. And the second shortest path, or at least 1 second shortest path, would be that one. And now, however, we have, if I interpret this in terms of tracking, it means that I have 2 cells that merge over time. Now, in biology, generally cells can divide, but they cannot merge. And here, moreover, I had said that I don't even want to allow for divisions, let alone for mergers. So I'm not happy with the shortest path solution either. because it can use a single edge more than once. So what we need is somehow the idea that we want to count how often an edge is being used, and we want to disallow an edge or a detection to be used more than once. And this can be thought of as an upper limit or a capacity on each edge. And this is where we come to flows of objects. And indeed, there is a min-cost flow formulation of this tracking by assignment. It assumes that costs are additive along paths, and the important thing, it also enforces the laws of conservation, and of course what I just said makes sure that each edge is used only once if this is something that I want to enforce in my tracking model. Good, so here's just a copy of the same graph, and now I've made this graph a little bit more complicated. I have replicated the detections at t-1, I've replicated the detections at t, and I have replicated the detections at t+1. Why? Because so far I had numbers written on these edges, but sometimes I also want to express that some detections are more plausible than others. Yeah, so maybe I want to say that actually the first detection looked pretty good. So let's say I'm giving this a -1 cost, so a reward of 1 unit. But the next detection, it didn't look that good, and maybe I want to charge a penalty of +2 if anybody wants to use that detection. Okay, and so these extra edges, on the one hand, they allow me to put costs on what I've drawn here are the blue edges, and I've written that blue edges may carry the cost or the reward of accepting a particular detection. And moreover, it allows me to impose this upper limit of how often a particular detection is being used. Note that it's not enough necessarily to put this kind of constraint on the edges only. Because if, for example, I could say, let's give this a cost of 0 here, I could say that, all right, let's say for the thick edges here, I could say that they all have a capacity of 1. So thick edges so that means I only want to allow to send 1 unit of flow along these edges. But as you see, it was still here possible for 2 tracks to use the same detection, right? Because it's, 2 coming in, 2 coming out. I've respected my capacity constraints, but it violates the assumption that I can make, if I want to, that each detection should represent just a single object. And if I do want to enforce the fact that each detection should hold just a single object, and I can or cannot decide to do that, then to all these edges which are shown in blue in this graph, I can give those an upper limit on their capacity. Yeah, so this is what I wrote here on the very right hand side. For the blue edges, they may express the cost or reward of accepting a detection. And in addition, I can impose that these have a capacity of just 1 if I want each detection to represent just a single particle. Good. Then the red edges we've already studied. They may carry the cost or reward of making an assignment. And this is already very good. And let's see what would happen here. what's the overall best solution? So if we use this one here, this one will incur a cost of -1 along its path, and this one here will incur a cost of -1 along its path. And I think that any other combination would be more expensive. I'm not totally sure, right? I mean, there are many paths, but just glancing at it, to me it looks like this would be the optimal solution here, and hence would encode the tracks that I want to get out. Do you have any questions so far? I want to talk about a particular twist now in this modeling. Namely, sometimes we do need to allow for spontaneous appearance of things. For example, yes, I want to track cells. I have this finite field of view of my microscope, and then a cell can walk into this field of view, or it can walk out of the field of view. So I need to somehow make allowance for this in my model. Well, and the way we do it here is that to allow for spontaneous appearance, I would introduce extra edges from the source to these places where something could spontaneously appear. And now these edges also need to be associated with some cost, because, well, if I gave these edges a 0 cost, then the algorithm could decide to just let cells appear and disappear. I should talk about the disappearing edges also, from frame to frame, and then I don't really have a valid tracking. That's not very interesting. Let's add the disappearing edges here. The disappearing edges give me an early exit from my model to the target. All right, I've drawn each and every one of them. So we need to give an appropriate cost to these extra edges, or otherwise my model will just use them all of the time and will not produce any reasonable tracks. Good, so now I have a minimum cost flow model of tracking by assignment for targets that cannot divide. And well, now I pretended that the yellow solution here is the optimal one, and perhaps it is, but once your graph gets bigger, of course, you want to solve this automatically. And hence, this is a good moment to talk about the optimization problem that we see here. So the graph above, I call it G. It's a graph with vertices V and edges E. And now my optimal solution will be, well, a solution to the following optimization problem. I'm going to sum over all edges in my graph, and for each edge I multiply the cost of using it with how often it is being used, with the flow across the edge. And I want to minimize here this flow along an edge times cost of an edge, summed over all edges. Now, if I did just this with no extra constraints, then I would not get proper flows from source to target. So things could just spontaneously appear and disappear along the way. So what I need are, on the one hand, conservation constraints. If you look at a single node V, I have this is a directed graph. Actually, I did not put arrows everywhere, but this is directed. Yeah? So time has a the arrow of time has a direction, and I only want to allow for now. Anyway, for the turquoise and purple ones, I also need these arrows. So for any node V in the graph, except the source and the target, I want the incoming flow to equal the outgoing flow to make sure that targets don't spontaneously appear or disappear along the route. And I saw there's a question in the chat. I'll come to it later. Okay. And so what do we do is for a particular for one node V in the set of all nodes, I look at all incoming flows. So I sum over all nodes U that are directly connected to node V. So I'm writing summation over U such that the edge UV is in the set of edges. And I'm summing over their flow. And I want this flow to be identical to the sum of the outgoing flows. And then this needs to hold for all vertices in the graph except S and T, or we can even make it to hold for S and T if I create another connection from T to S. So let's say here without S and T. Then I want to be able to say that for a particular edge E, the flow should not exceed a certain upper limit, which I've called here BE as the bottleneck associated with edge E. And in the example I gave, this limit was 1, so that one cannot send more than one object along each edge. And then, well, if it's a tracking problem, then I don't want an answer like half a pedestrian went left and half a pedestrian went right. I just want to know, so pedestrians tend to stay integer. So I want these flows, in this example where I just admit 1 unit per edge, I want them to be either 0 or 1, but not some fractional number in between. All right, now in terms of constraints, the last one is a mean one because it's non-convex, making the problem a purely combinatorial one. And I will show you later in as much detail as time allows that actually for min-cost flow problems, we don't need to use this kind of non-convex constraint, but we can instead use just the convex requirement that the flow should be non-negative. And that makes for a huge simplification of the optimization problem. Or let's say that means that it belongs to a different and much easier to solve class of optimization problems. All right. So do you have questions about how the graph above, how it maps to this equation here? So in the chat there was this excellent comment that what I had highlighted here in yellow was not the optimal solution, because if I just look at the contribution from this first part here, the way I had picked, there was one edge with a cost of 0 and one edge with a cost of +1 that was used. It makes it for a total cost of +1. And if instead I use the green edges, this one and this one, then the total cost would be just 1/2, which is lower. And hence the optimal tracks are not the yellow ones, but the green ones. And this is what we need clever students for, and this is what we, if computer vision scientists are not reliable, then this is what we need the optimization problem for. So we can solve this automatically and with a certificate of optimality. So do you have questions for this formulation here? All right. Then last thing I want to point out before the break is that this is one instance of a much bigger and extremely well-known, extremely important class of optimization problems, namely those of linear programs, or if you use the integrality constraint, of integer linear programs. So what you see in this black box here is the standard form or canonical form, and the conventions on how to call this differ a little bit, of a linear program. So we are, why is it called linear program? Because we're minimizing over a vector x, and the objective function is linear in x. And well, if we had no constraints, then there would, that would be an unbounded problem. Yeah? So the optimum solution x would go in the, because we try to minimize, in the opposite direction of the cost vector c, and would lie, infinitely far away in the opposite direction of c. But to make it more interesting, we have these constraints, which are also linear, hence linear program. Yeah? So A is a matrix times vector x should be no more than vector b, and x should be non-negative. Again, this is a matter of convention, because this constraint, in principle, you could integrate it in the constraint above, but this is the standard form. So the black thing is a linear program, and if in addition one wants to admit only integer solutions x, then it is called an integer linear program. And down here I did not really talk about graphs and edges, so maybe I should call this here the dimension of x. Yeah, so z here just means the Cartesian lattice, or the integral lattice, which has as many dimensions as x has. And a linear program, hugely important class of optimization problems, can be solved in polynomial time and very efficiently in practice, and integer linear programs can be extremely hard to solve. So summary of this part: we can model tracking by assignment as a minimum cost flow problem. Minimum cost flow problem is a special instance of an integer, or as it turns out, actually of a linear program, a globally optimal solution of which can be found efficiently. Good. So this is good news. It means that if we have a tracking problem, if we have a method to give us detections, if we have a method to give us costs for these various assignments, and the old manual hard coding way of things would be to use prior knowledge to find these costs. So for example, we could consider these distances, and that's also a little bit what I try to do in this plot here, that bigger distances tend to have bigger costs. But you can also take into account things like, all right, there's a detection here, there's a detection there. How similar are they in appearance? If they're very dissimilar in appearance, then probably you want a high association cost. Yeah? So for example, if this was a person dressed in white, and this was a person dressed in blue, then that doesn't look like a very good association, because how, you don't really expect the person's dress to change from white to blue in a single time step. Given such a graph, we can then find the optimal solution very efficiently. This is the bottom line of what we've just seen.